This is the problem-solving part of lecture 11 on isomorphisms. Let's see, I'll do 1, 2, 3, 4, 5, 6, 7, 8, 9. And there are 22 questions, so a bit under half. It's important. Now, yeah, it's a lot. This is already a very long lecture. An important one. Isomorphism, very important concept in group theory, finite group theory. So some of these questions I will do rather cursorily, right? Leave you to fill in the details. Actually, so question 1 is determine whether or not the following direct products, so Z2 times Z2 question mark Z4. Right? Now, can you remember a theorem? Now, I'll just sort of discuss it rather than leave you to do the details. But can you remember a theorem where a way to prove that something is not, two groups are not isomorphic, is to look for the number of solutions to the problem, you know, some element x to some integer. So the number of solutions x to so that equals e. So let's try to prove that these two groups are not isomorphic. Now I've written up this table several times in earlier lectures. So go to the table, and you'll notice that for every element of this set, call it a squared is e. Right? And for this, this is a cyclic group of order 4, and so it has a generator of order 4. I mean, in a cyclic group, the order of the generator, that's an element, right? So the order of the special element that's the generator, that order will be equal to the order of the group. Right? That makes sense because that generator creates the whole group. Right? So there's an element here that's of order 4. So call that, that's the generator G. So G the fourth is E. Okay, but this one has no elements that of order 4, right? Because all of them are order 2. So you'll get a difference for this solution where n is 4. All right. So therefore, these two. The answer to question 1 is these two groups are not isomorphic. Right. It was about a half an hour proof, right? Okay. So here we've actually used it. Question 2, determine whether or not Z, again it's using this product group, so it's question 2, question 1, so Z2 times Z2 isomorphic, question 2, the group V. V stands for vier, a German word, means 4. The Viergruppe in German, the 4 group. Now, what is it? It's the group you get from symmetry rotations of a rectangle. Okay, so when you're rotating a rectangle, it'll have 4 operations, 4 members of the set. There's the do nothing, that's your I, that's your unit. There's rotating by 180 that way, right? You could call that I don't know, R. And there are 2 symmetry operations by rotation about axes. There's that one, okay, and then there's that one, and that's it. That's the 4 symmetry operations. So construct the group table. Do it as an exercise. So it'll be have 4x4, 16 entries. And then compare the group table you get here with the group table you get here. And just by inspection, I mean, you don't have to swap rows or columns or anything, you'll see that these 2 groups are isomorphic. Just by translation. Just translate the terms in this table into this one, or vice versa. And you get the identical group table, right? So by definition, these 2 are isomorphic. So the answer for 2 is yes, they are isomorphic. Okay, question 4. G is a group. You're mapping G into G. So that's question 4. So here's your mapper, your function, and it maps G into itself. Right. And your f of x is just a member of G's, and you're told that that's equal to G of x, G inverse xg. Okay. Prove that this function, defined by this, okay, is an isomorphism of G unto itself. Okay, so we have to show that this f is an isomorphic mapping. Now, by the way, if you have an isomorphism from G to itself, that happens often enough. It's given a special label. That type of isomorphism is called an auto, like self, automorphism, like automobile, self-powered vehicle. So an automorphism is an isomorphism of a group to itself, hence self or auto. Like automorphism is short for like isomorphism. So this is an example, well, assuming that it is an isomorphism, is an example of an automorphism. All right. Well, let's try to prove that. Let's see. What's question 4? Is it well formed? Yeah, the usual thing. Well formed. Is it bijective? And is it the f of n thing? I don't even know what to call that. All right. Okay, is it bijective? Now so this is your G, this is your G. Let's take an arbitrary element Y here. So we're working on well formed seems pretty trivial, right? Whatever x you have the same x in here. I don't think there's any discussion about being well formed. It seems to make perfect sense. All right. So let's work on surjective as part of the bijective proof. So find me some element here that maps to that'll give me y given this, right? So well, how about this? Let this point be g of y, g inverse. And you may say, so for any y, assuming this maps, let's test that. So f of g, y, g inverse, using this definition, so that'll be g inverse, whatever this is, g, y, g inverse, and then you put a g here, okay? Well, can you see that that's just y? So that'll be g inverse g, y, g inverse g. So that's just e, y, e, which is just y. Okay? So for any element here, there's a corresponding element here that gets mapped from to y. Okay? So for any y, g, what is g? Is little g a member of the group? Yes. Let G be a fixed element of big G. Right. Okay, so that's general. So for any y here, you can find a corresponding term here, some this element here, and it's well formed. Well, there's some discussion. It is well formed because this belongs to this group. Okay, so because G and Y belong to G, the domain. All right. Okay, so we've found. So for any element here, there's a corresponding element in the domain. So in other words, any element here gets mapped to. So all elements get mapped to. Therefore, by definition, it is surjective. Now, we can use that theorem. We use it many times now. If the size of your two groups are the same, well, they obviously are because they're the same group. Okay. So if the size of the two groups, in this case one group, are the same, and if your mapping, your F here, if this F is surjective, therefore I think that's theorem 27. If the mapping is surjective, therefore it's injective. Okay. Well, we've just shown that it's surjective, therefore it's injective, therefore it's bijective. Okay. So we've done two of the three things. Well-formed bijective. Now we need to do that f of mn thing. So, we need to show that this is equal to fm fn. Right? And you need that to show that the corresponding elements in the table map. Okay. So what is So F, now, so for a general M, okay, now let's just put now